Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of CUDA Crash Course, we're going to be talking about the optimization process for CUDA applications. And we're going to be kind of going step by step with matrix multiplication just to see, how far we can push matrix multiplication in terms of performance. And incrementally showing, different speedups we get from different strategies. So in this video, we're going to focus on all the optimizations we can do before we start getting to shared memory. Now, there's other optimizations as well that aren't included here, but it's important to kind of scale back and limit to a couple of the major ones that we can look at. So we're going to be starting off with the baseline, right? So it's always important we start off with this is where we're at, and this is kind of what to expect, right? So in a very baseline version of matrix multiplication, we have that implemented here in this naive directory. So all of these results are posted online at github.com/coffeebeforearch. So the first thing we're going to look at is a very basic implementation. So here we've got matrix multiplication in global memory. So again, we're not using shared memory here. We calculate a row and a column, right? So every single thread is going to map to one output element in the C matrix. And then we accumulate inside of the C matrix, all these temporary results. And so by the time this for loop completes, we've got our final result in our C matrix. So how does the main function look? A lot of basic things. So you see, we're not going to be using unified memory here because we really want to isolate the performance here. We don't want, maybe sometimes we get lucky in terms of page faults. We don't want any of those errors. We really just want to see what the performance is of the kernel in isolation. So here we've got calloc here. This is just to make sure that our C matrix is initialized to all zeros, right? And you see that we're using 16 by 16 thread blocks, so 256 threads per thread block, 16 in the X direction, 16 in the Y direction. And then here you see we pad out the number of blocks we need in both dimensions. So we launch blocks, comma, blocks, right? So this dim3 is just a struct with 3 fields, an X, Y, and a Z. And then we launch our kernel, and we don't need to verify the result every time. So I verified the functional correctness of this. That way I don't have to verify it on these really large matrices. So all these performance results are for a 4096, or rather a 2 to the 14 by 2 to the 14 matrix. Right, so this is pretty big. Each matrix is going to be a gigabyte in size, right? So a gigabyte for A, a gigabyte for B, and a gigabyte for C, right? So pretty long computation here. So with this basic version, what is our baseline? So in results.txt, so this is run on a GV100 GPU. So it's a Volta architecture, pretty big machine, or big GPU, right? And we get about 13 seconds, right? So we don't really have any context is this good, is this bad, but our baseline is going to be 13 seconds. So what's an easy optimization we can do? Now, the first thing we can look at is how do we maybe get rid of some unnecessary writes to memory. So let's open up this temp var one, and you see the only difference that we do here is that instead of writing back to memory every single time into C, we go ahead and use this temporary variable. Pretty simple idea. Now, what's the thought behind this? Well, if we can have temp and say a register, that means all we're doing is updating a register each iteration of this loop. That means we're not having to access memory. Hopefully we hit on it in the L1 cache. Maybe we don't. Maybe we even miss in the L2 cache. In this way, we can just avoid that altogether, have it in a register, and then eventually have one write back. So we basically took, in writes into memory with just a single write per thread. And you have to remember, if we're launching, 2 to the 14 by 2 to the 14 threads, that means we're going to have 2 to the 14 times 2 to the 14 times 2 to the 14 writes to memory, right? Because we've got each of those threads will all be doing in iterations of this loop, right? So we save all that. What does it give us in terms of performance? Well, here's our results, right, from one run. And you see we're down from like 13 seconds all the way down to 5 seconds. Right? So that's pretty good, right? So we've already improved this quite a lot with, just about 2 or so lines of code, right? So we're seeing some basic optimizations here in terms of just eliminating some unnecessary work. But we can do even better than that. And again, this is all without shared memory. So what else can we do? Well, one thing that we didn't really talk about was our grid size, right? So grid size is a very, very important thing in GPUs and how we kind of lay out our problem and how that translates to performance. So let's go ahead and we'll kind of switch over. So this is basically what matrix multiplication looks like. We've got an A matrix, we've got a B matrix, and then we have our C matrix. And every single thread will end up following this pattern of these orange lines. So it will go across the rows of this matrix, of the A matrix, and down the column of a B matrix, right? And so if we just added more orange lines, that would correspond to different elements of matrix multiplication, right? So each thread gets mapped to the C, so we'd have one thread here would follow this exact pair, right? So this row and this column. Okay, so what's a problem with our current implementation? So right now, right, if we go ahead and consider that we have, one thread block here, right? So that's going to correspond to just a chunk of our final matrix C. That thread block itself, so if we kind of expand this out, we'll have, 16 threads in this dimension, 16 threads in this dimension, right? So we go 16, blah, 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 all the way to 16. And then we'll have, more in that dimension. And let's go ahead and use a different color for this next row, maybe orange, right? And then a couple dots, right? So now we've got these purple threads, right? So from 0 to 15, and then we have the orange threads from 0 to 15. Now it's important to know that the SIMD width, or the width of the hardware, is actually 32, right? So you may have heard about warps, right? And warps are collections of 32 threads that execute together. So what happens, even if you have a 2D thread block or a 3D thread block, inside of hardware, it has to get translated to, a one-dimensional thing, right? So all that thread ID X, thread ID Y, thread ID Z, those just correspond to values loaded from some special registers, right? For, TIDs, right? Or thread IDs. So inside of the hardware, it'll take some 2D arrangement like this of threads, and it will go ahead and linearize it. And so how does that look? Well, here we've got 16 threads in the first row, 16 threads in the next row. So if it wants to make a warp of 32 threads, all it does is it pieces them together. So we'll have, we'll have the 16 threads from this row, and they'll get shoved together with the next row, right? So the 16 threads from the next row. So what's wrong with this? There's nothing inherently wrong with this. So if we think in terms of things like control flow divergence, if say the purple threads went one direction and the orange threads went another direction, in terms of if we hit an if statement, some of them go in the if, some don't, what would end up happening is only 16 of the threads maybe would be active at any given moment. So effectively, those two control flow paths get serialized, right? So we don't have that in this case because all the threads are going the exact same control flow path. So no control flow divergence. But we do have is memory divergence though. So what ends up happening is these 16 threads will be accessing, row 0. And these 16 threads will be accessing row 1. And this is going to happen for every single warp because every single warp is going to be two of these rows of the thread blocks mixed together. So what's wrong with this? Well, now every single time we want to execute an instruction, so if we want to do, a read or we want to do a write or something from this A matrix here, right? They're going to be accessing two completely different rows, right? And that's a real problem because that means we need two memory requests before all these 32 threads can even begin execution, right? So how do we fix this? Well, there's a pretty easy way. What if we just increase the thread block size, right? So we just make it, say, 32 by 32 now. So now, all of these purple threads, right, will have all the way here now, these will be 32 threads, right? So an entire warp will be made of the exact same row of, in this case, the A matrix, right? Which is really good for us because that means they'll be accessing one big consecutive chunk of memory. And if you're unfamiliar with how the GPU memory system works, all of these threads, you would think maybe, if you're unfamiliar with GPU architecture, okay, 32 threads all accessing part of A, 32 transactions, right? But there's this thing called a coalescer, right? And what that does is it'll say, okay, all these 32 threads are trying to access the exact same or, a consecutive chunk of memory. Well, instead of doing 32 requests, I can do one big request, right? So this will, say, lead to one request from memory, right? And it will load in a 128-byte cache line. So the L1 cache works on 128-byte cache lines, and that's for a very specific reason. So typically we're using things like ints or floats. Floats are 4 bytes, ints are 4 bytes. If we translate that to 32 threads, which is our SIMD width, if each 32 threads loads in 4 elements or 4 bytes, right, or requires 4 bytes, 32 times 4 is 128, right? So one cache line fits all the ints or all the floats for a particular warp, right? So if we just change these size, all of a sudden we guarantee that we can get this one request instead of 2 requests. And so that's what we have here, right? So if we go ahead and go to coalesce accesses, all we've done is we've changed one line of code again, right? So now we've got, instead of our thread block size being 16 by 16, it's now 32 by 32. Right, so just a single number change. And as just a refresher, if we go back, we go to temp var results. So we were at 5.1 seconds here, down from 13 seconds. And so once we start doing coalesced accesses, we see we're down to 4.25. So we've improved performance by about 0.75 seconds, right? So again, pretty good, right? We have almost about an entire second of an improvement just by changing a single number, right, and understanding how the hardware works. But, of course, we can do better, right? So how do we do better? So let's go ahead and get exit out of there. We'll go back. So the next thing we can think about, even without using shared memory, we can still do some prefetching, right? So what are we going to take advantage of? So let's go back to our picture. So what we're going to go ahead and take advantage of is this idea that, let's go ahead and zoom back, get rid of these. We're going to take advantage of the fact that inside of the A matrix, for all the threads that are mapped to the top row of the C matrix, at any given moment, all these threads will be accessing one element of A, but they'll be mapped to the different columns of B, right? Well, okay, so if all 32 threads inside of the A matrix are going to load in, 32 different columns of B, but only one element of A, why don't we load in a couple of the elements of A ahead of time, right? So we'll already be kind of using up, all of our, parallelism here. So let's try to use some more inside of A. So instead of loading one element from A for every 32 elements of B, why don't we load in 4 elements of A? So this is kind of a form of loop unrolling. So let's go back to our code. We'll go to prefetch, and we'll see how we do that. Right, so if we understand some of the more modern features of the language, say vectorized memory accesses, we can go ahead and load an int4. All an int4 is 4 integers, right? It's a struct with 4 fields, x, y, z, and w. But what this does is it generates a wide vectorized load. So instead of loading 32 bits, right, say for a single int, or 64 bits maybe, like a load 64 for 2 integers, this guarantees that we can get a 128-bit load, so a LD64. Right, so in this case, we'll load in 4 elements from A, and we'll just play some tricks with casting here. So we'll pretend that our big array of integers is actually an array of int4s, and so we'll load in one of these int4s, and that way we kind of shrunk our loop. So now it increments by 4 every single time, so we basically unrolled the loop by 4. So we'll load in 4 elements, we'll put them in A temp, and then here's our 4 computations. So instead of having 4 different iterations of the loop, we're now going to access X, Y, Z, and W. And these are coming from a single memory access, that's this wide memory access right here. And then B stays the same. We just have to increment I every single time like it would normally be. So 0, 1, 2, 3, because it gets shifted over by 4 every single time. Okay, so a little bit more complicated than the last couple of optimizations, but nothing really too fancy here. All we're doing is we're saying, okay, well, when I'm accessing the B matrix, right, for every single warp, it's going to be loading in 32 elements from the B matrix, but it's only accessing one element from the A matrix. Well, I've got wide hardware. Why don't I start loading in extra elements from that A matrix ahead of time, especially if I can do them in a single access, which is what we do here with this int4. So what does this do for us? So again, let's see what we did with the last optimization. So we did coalesced accesses, results.txt. We got 4.25, about 4.26 seconds, right? And so now we went from 4.26 to 3.5, right? So again, about 0.75 seconds, so about 3/4 of a second decrease just from doing a little bit of prefetching here and making sure that we're using the hardware effectively. We know we can do, vectorized loads in some circumstances. Maybe the compiler isn't smart enough to figure that out for us. So if we can help the compiler along, well, we just gained another, 3/4 of a second, basically with not too much effort. But of course, we can still do better, right? So now what have we done? Let's kind of recap a couple of the things. So we went from a baseline version. The next thing we did was we accumulated a temporary variable to limit the number of accesses to memory we have, or unnecessary accesses. Then we saw that we could get better coalescing if we just made sure that all of our threads in each warp were on the same cache line. Then we saw that, if we went ahead and prefetched some elements ahead of time and used these wide vectorized loads, we could get even more improvement. Now let's see what we can do with some unrolling that's not manual, right? We don't always want to do some manual unrolling. Sometimes it's necessary because the compiler isn't smart enough to unroll the loop properly, but it turns out sometimes it's okay. So we can add just a single line for some circumstances. So we can add this pragma unroll, and it will attempt to fully unroll this loop, right? So if you're unfamiliar with loop unrolling, instead of having a loop, it just basically puts all of the iterations of the loop one after each other, right, inside of the actual assembly, right? And it gets rid of some of the loop overhead of, say, doing conditional checks, incrementing loop counters. You just have all the code there. So your code gets bigger, but you get rid of some of these checks, right? And you can even specify this. So you can say unroll 1, right, which basically just means don't unroll the loop. You can unroll it twice, 4 times, etc., or you can try to fully unroll the loop. So nothing else has changed, right? So the grid size stays the exact same, the thread block size, all this prefetching stays the exact same. All we're doing is we tell the compiler with this pragma, hey, unroll this loop. So again, we'll go back to the prefetch and we'll look at the results. We were at about 3.5 seconds, right? And here, right, we're down to about 3.36 seconds, right? So it's not a huge improvement, but again, it's a single line of code. And it is stable around this, so this isn't just an individual run thing. I tested across a couple of runs. It'll vary slightly, between each run, but about, 150 millisecond improvement for that single pragma. Now, this is, a lot of this is kind of like, okay, well, why are we trying so hard to improve matrix multiplication without using shared memory? And the real key point behind this is, what's actually better? Is it better to, spend all this time doing all these crazy optimizations, or maybe not so crazy optimizations, without using shared memory, or should I just use shared memory? And the real kind of lesson to be learned here is that it's just really important to understand the hardware. So let's go to a naive, go back a directory. So let's go to a naive shared memory implementation, right? So here, this was from another example that I did in the CUDA Crash Course series, and it basically just does, basic matrix multiplication using shared memory. It uses 16 by 16 thread blocks, and here you see it just iterates the tile over, loads in the values, and then computes on the individual tiles before loading in a new tile, right? And again, like I said, it uses 16 by 16 thread blocks, which we already showed, is not ideal, right? We can do better if we maybe make them 32 by 32. So let's see what happens if we just throw shared memory at it without considering maybe any of these other details. So I've got the results here for a 2 to the 14 by 2 to the 14 matrix, and it's about 3.5 seconds, right? So to put this in perspective, I went ahead and plotted these out, these different optimization stages, and I've got them right here. So here's our baseline at about 13 seconds. We get it down to about 5.1 seconds by adding a temporary variable. coalescing from 5.1 to 4.25, so a little less than a second here, maybe about 0.85 seconds. Another 0.75 seconds by doing some prefetching. Another 0.1, 0.15 seconds or so, 0.16 seconds from doing this loop unrolling. And we see that kind of naive tiled approach, it's at 3.5 seconds, right? So that's worse than even just the prefetch version, right? So, the key point here is it's really important to understand your hardware and understand why you're writing the code that you are and how that's going to translate to performance. So on different machines, like I said, you may not see quite as drastic speed ups. Even at different matrix size, you'll see a different, speed up potentially. But the important thing is understanding why that speed up is occurring, right? So between the baseline and the temp, we're just having less writes to memory, right? So we're just having a single write at the end of execution. And when we have a ton of threads, that's way less writes, or way fewer writes. When we're coalescing, we're making sure that we're not generating excess, reads from memory. We just need to read, one time for each warp now. With prefetching, we're making better use of our hardware by doing these wide vectorized loads, right? And then we have these values available to us ahead of time. And then with loop unrolling, we're getting rid of some extra loop overhead just by understanding what the compiler can do, right? And this is without using, cache tiling at all. So in the later videos in the series, or in the next time we do one of these, we'll show all the kind of really cool optimizations we can do in shared memory and really see how fast we can push matrix multiplication, with all of these, with our big toolbox of optimization strategies. But that's going to go ahead and do it for this video. I'll go ahead and link down to the spreadsheet. And again, inside at github.com/coffeebeforearch, if we go into CUDA programming, I've got all the code for all of these things in here. So if we go into plotting, matrix mul, and then this is the version 2 of these performance things, I've got links to all the different, all of these different benchmarks that I've used, and as well as the results from the profiler. So this again was from a GV100 GPU. So again, results may vary depending on your architecture. So feel free to check those out as well. But that's going to do it for today. As always, I'm Nick, and I hope you have a nice day.